Hello, everyone. Welcome to today's ACM Tech Talk with Hadley Wickham. This webcast is part of ACM's commitment to lifelong learning and professional development for a global membership of scientists, programmers, designers, and managers. I'm Andrew Conklin, Director of Engineering at Origin Data Sciences, where I work on predictive analytics services and patient disease progression for clinical trials. I'm a lifetime ACM member, currently serving on the ACM Practitioners Board. For those of you who may be new to ACM, we have a few highlights for you. ACM members can stay competitive in the constantly changing world of computing with a range of Learning Center resources at learning.acm.org. ACM has recently updated our Code of Ethics with a collection of principles and guidelines designed to help make ethical, responsible decisions in practice. Our numbers section gives us an idea of ACM's global impact. We can see here the number of content readers globally each year, our number of citations in the digital library, as well as our award winners, ACM fellows, and global conferences and events. ACM provides timely content, including Communications of ACM and Q magazines, access to the digital library, the world's most comprehensive database of computing literature, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to mention a quick upfront FAQ. First, the slides will advance automatically for you. On the bottom panel, you will find a number of additional widgets and resources. You can use the Facebook and Twitter widgets to share the presentation link, as well as tweet comments and questions using the hashtag ACM Learning. We'll be following for your tweets live. We also have a community discourse page to continue the discussion after this webcast, including questions we won't be able to get to during the Q&A portion. If you have any questions during this talk, please type them into the Q&A box at any time and click the submit button. I'll organize the questions as Hadley speaks, and he'll reserve time at the end of the presentation to address them. If you are experiencing problems with the slides or audio, try refreshing or closing the web browser page and relaunching the presentation. To control volume, use your computer master volume. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available, and check learningacm.org for updates on this and upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it out to help improve our tech talks. You may also open the link to the survey at any time from the resources window on your screen. Today's presentation is The Joy of Functional Programming for Data Science by Hadley Wickham. Hadley is Chief Scientist at RStudio, a member of the R Foundation, an adjunct professor at Stanford University and the University of Auckland. He builds tools, both computational and cognitive, to make data science easier, faster, and more fun. His work includes packages for data science, principled software development. He's also a writer, educator, and speaker promoting the use of R for the data science community. Hadley, without further delay, please take it away.
Thanks, Andrew. Oops, I think I just shared. Okay, you're sharing the right screen, right? You can see the joy of functional programming. We'll assume yes, unless I hear otherwise. So today I wanted to talk a little bit about one of my kind of favorite programming paradigms, which is functional programming. Now, over the years, I've struggled a lot to define exactly what functional programming is. It's really hard to do so in kind of a precise way that still makes sense if you don't have a bunch of computer science jargon loaded in your head. So today I'm not really going to talk about exactly what functional programming is. It's programming with functions. That's about the level of definition we're going to do today. But what I want to do is kind of show you like why I think it's really cool, why I like it, particularly for data science, and then show you a bunch of examples using functional programming and R to solve some real data science problems. And To be clear, this talk is motivated by the joy of cooking, not the joy of sex. So there's going to be a bunch of baking and baking examples today. So pictures of baking, drawings of baking. We're going to have baking examples, and hopefully this will help some of the more abstract ideas stick in your brain a little bit better. And so I'm going to talk about functional programming in the context of data science. And this is kind of my model of the data science process. So you're going to import your data, you're going to do some work to put it in, get it and tidy it up into a format that makes the rest of the analysis easier. You're going to do a bunch of transformation, a bunch of modeling, a bunch of visualization. And then eventually you're going to decide you've got the insights out of the data you need, and then you're going to go and communicate that to others. And to me, one of the things that distinguishes data science from related fields like data analysis is that data science is fundamentally an activity you do in a programming language. And so today, what I'm going to talk about is this idea of functional programming, which I think is particularly helpful for two parts of this process, of which I'm going to illustrate. So it can be really, really useful when you're importing your data, when you've got a bunch of unruly spreadsheets or flat files or multiple SQL queries. You've got to wrangle them all together into one format. And then also at the very other end of the spectrum, I want to talk a little bit about how you can use functional programming to produce multiple reports. So how can you create a report for one person or one city or 1 year, and then use functional programming to generalize that to a report for every person, for every year, for every city. And I'm going to be talking about this primarily in R. If you're not familiar with R, I'm going to try and explain kind of some of the bits of R syntax that might be unfamiliar. If you are familiar with R, hopefully I'll also give you a few new tips and tricks to take away with you. But today we're going to be working primarily with the purrr package. Purrr, the idea of purrr is to help make your functional programming skills purr in R, hence the cat logo. So to start with, I wanted to start with a little bit of motivation. And I think this is a really common pattern that you have a bunch of CSV files in a directory. So here I'm going to use the dir function in R. That's just going to list all of the files in the current directory that match this pattern, this regular expression, i.e. the CSV files. I'm going to save that to this path thing using this arrow. This is what we use in R for assignment. So often I'll read this as gets, like path. The path here gets the value of the dir function. And now I want to read all of these in. And I want to read each of these in as a CSV file. So I'm going to use the read.csv function, which even if you've never used R before, hopefully you can guess what it does. And then I'm going to save each of them into a list of data frames, which I'll explain a little bit more shortly. So R uses this assignment arrow. You can also use equals for assignment, but I think it's generally idiomatic to use this arrow guy. Now in R, as in pretty much every language, there's typically 3 components to your for loop. So the first thing you're going to do is create the data structure where you're going to put the output. So here I'm going to use the vector function in R. That's going to create a vector of type list in this case that has one element for every element in that vector of paths. So I'm creating a list, which in R is the most general data structure because you can put any other data structure in R inside a list. So this is going to be an empty list. Now we want to fill it in. So the second thing we're going to do is provide a vector to iterate over. So we're using this function called sequence along, that is going to give us an integer vector from 1 to the length of paths. So if you are an R user, you might also be familiar with this colon notation, which does a very similar thing. Generally, you should avoid that in your for loops, particularly if they're inside functions or packages, because it's going to fail in an unpleasant way if there are no matching CSV files, if path is length 0. So the first thing is we create a place to store the output. The second thing is what we're going to iterate over. And then the third thing is the code that is going to be run in every iteration. So we're going to read the CSV file. Where's that CSV come from? Well, here's another little bit of our syntax. We use this double square brackets to extract the ith element from the path selector. So this is going to count 1, 2, 3, 4, 5, 6, 7, all the way up to the number of paths. We extract that path, we read that as a CSV, and then we save it back into the data structure. And if you have used R before, you might be wondering, well, why am I using the double brackets here rather than the single brackets? I think it's really good a principle to always use the double square brackets whenever you're getting or setting a single element, and reserve the single square brackets for whenever you're working with multiple elements. That just makes your code a little bit clearer and less ambiguous. Now, before I go on to talk about these functional programming ideas, there's like absolutely nothing wrong with using a loop. You should never feel bad about using a loop. You should, in fact, I think, never feel bad about any code, no matter how ugly you might think it is, as long as it gets the job done. But I think by learning a little bit about functional programming, you can write code more quickly that more succinctly expresses the ideas that you really care about. So here we're going to talk about this. Today we'll talk a bunch about this map function, which does exactly the same thing as the previous for loop. And one of the reasons we're going to talk about that is because there's a bunch of convenient extensions. So instead of returning a list, we can return a data frame or various other types of things. So, like, why shouldn't you use a for loop? Well, to talk about that, I want to talk a little bit about cupcakes. So maybe you've never made cupcakes before. Maybe you've made millions of cupcakes, but this is like a basic cupcake recipe. This is a cupcake recipe that I have made. It's a totally legitimate recipe. But it's a recipe that's kind of aimed at people who are not very familiar with baking, because it's very, very explicit. So for example, it tells you exactly what to put the ingredients in and how to mix it together. And this is great when you first start out baking, but over time, it starts to be a bit of a drag, because over time, you're like, well, I've made vanilla cupcakes a million times now. I want to do something else. I want to make chocolate cupcakes. And so what you might be interested in is like, well, what's the difference? What's the difference between vanilla cupcakes and chocolate cupcakes? And if I kind of flick back and forth between these a few times, you'll notice that they seem pretty similar, right? And in fact, the main difference, unsurprisingly, is that chocolate cupcakes also have cocoa powder in. And this is one of my kind of frustrations with this recipe book in particular, is that this is a recipe book that tells you how to make like 50 different cupcakes, where 95% of each cupcake is exactly the same. And I think that's a bit of a shame, because it means it makes it harder to figure out, how do you generalize? How do you take what you've learned from making all these cupcakes and make new flavors of cupcakes? So what I want to do to this recipe is kind of refactor it, a little bit like you might refactor a function, to kind of make it a little bit easier to see what's going on and to make it easier to compare different cupcakes. So the first thing I'm going to do has, well, no real relevance to programming, but it's a funny story. And that is, like, when I first got this cookbook, I bought it because my best friend in New Zealand, who's a really good baker, recommended it to me. And I got it, and I made cupcakes out of it, and they didn't turn out very well. And I was like, oh, I must have just been having a bad day. So I tried it again in the future, and it still turned out bad. I was like, huh. This is kind of weird, because my friend's a really good baker. I'm a pretty good baker. Like, what's gone wrong? And it took me a long time to figure this out. And it wasn't until I actually visited her in New Zealand and looked at her copy of the cookbook and discovered that I have the American version of the cookbook, which has these ridiculous approximate volume-based measures, where the New Zealand cookbook has much more accurate weight measures. So the first thing I'm going to do is just convert this to proper measurements, proper units. And then the next thing I'm going to do is I'm going to assume that you've got a little bit of baking experience, that I can tell you to mix things together and you'll figure out how to do it. And again, this is kind of changing the audience a little bit. Now, this is not so accessible to someone who's never done baking before, but as long as I think you've done any sort of baking, not just cupcakes, but anything really, you'll be able to follow these instructions still. And now I can sort of start to use variables so that when I start adjusting the ingredients for other types of cupcake, the recipe can stay the same. Because basically all cupcakes have the same recipe. You beat the dry ingredients and the butter together, and then you mix in the wet ingredients. And what's neat about this is that this recipe and these ingredients are now small enough that I can put 2 recipes on one page. And what's nice about this is it makes it very easy to see precisely what is the difference between vanilla cupcakes and chocolate cupcakes. And you can see like all of the ingredients are exactly the same, except for the flour, where there's 20 grams less flour, and chocolate cupcakes have 20 grams more cocoa. So it's not that we're adding cocoa, it's that we're substituting flour for cocoa. And this isn't like the scientific discovery of the century, but I think this is kind of neat because it now gives us a knob we can twiddle. Like if those cupcakes were too chocolatey, just substitute less flour. Or if they weren't chocolatey enough, substitute more flour. Or if you're thinking like a scientist, you might be like, well, what happens if I substitute all of the flour for cocoa powder? I don't think you're very likely to get good cupcakes out of that, but I think that's a really interesting question. I think that's one of the things that you want to be thinking about, like when you're baking and when you're programming, like how do I generalize this to go beyond just these recipes I've given so that I can start to create my own recipes? And indeed, like now that we've got all this extra space, we can start to add other things. So if you want to make espresso cupcakes, well, all you have to do is dissolve some espresso powder in the milk. And as you look at more and more variations, this gives you a sense for like what are the knobs that you can twiddle if you want to create your own unique cupcake flavor. So what on earth does this have to do with functional programming? So I'm going to give you all a little challenge. I've got 2 for loops here. So again, they have that same structure as before. We first create the output, where we're going to put the output. This time it's going to be a vector of doubles of real numbers. We're going to iterate along the columns of this data frame, this mtcars data frame, which is moderately infamous if you're an R user. And then when we index into that, that's going to extract the column I. So what I want you to do is just take a minute, look at this code, and think about these for loops. Like, what do these for loops do? How are they the same? And how are they different? And I'll join you back in 1 minute. Okay, so hopefully you have identified what we're doing in these for loops is we're computing some summary of each column. So that's how both for loops are the same. They're both computing some summary. The first for loop is computing the mean, and the second for loop is computing the median. And that importance is really, really different, but it's a little bit hard to see that difference because so much of the code is the same. Just like with our cupcake recipes, it was difficult to see the difference between vanilla cupcakes and chocolate cupcakes because so much of the recipe was repeated. So what for loops kind of tend to do is emphasize the objects involved, when often what you're more interested in is the action. What is it that you are doing, computing a mean or computing a median? And so the idea of kind of functional programming, one of the aspects of functional programming that I think is really cool is that it tends to weigh the action and the objects kind of equally. So I'll explain what this code does a little bit later, what this means, but this is exactly the same code. This is exactly the same impact. Map says take each element of mtcars, compute the mean of it, and save the results back into a double vector. But what's nice about this is that the object and the action are on equal footing, and we can easily see the difference between these 2 lines of code. The other thing that I think that's nice here is that we can combine it with the pipe. And the pipe is just a way in R, it's sort of a type of syntactic sugar, which allows you to write the first argument of the function to the left of that function, like you're doing a pipeline of transformations. And so when you read, typically when you read the pipe, the easiest way to pronounce this in your head is as then. So take empty cars, then map over each element, storing the results in a double vector, applying the mean to each element. And this, I think, in combination with functional programming and in combination with harder problems, I think it admits some pretty elegant code for problems like this, where you take a data set, you split it up by one of the variables, then I'm going to map over each of those pieces to fit a linear model, then I'm going to extract the coefficients of that linear model out and store it all into a data frame. And so as you master the tools of functional programming, it allows you to express these ideas pretty succinctly and pretty elegantly. So that's kind of the theory. Now, I just want to remind you that, or just to say that, like, there's always a for loop somewhere. So all of these functions I'm going to show you, like, somewhere deep inside them is a for loop. The important thing to know is that someone has to write for loops, but it doesn't have to be you. And I think that's one of the things that at first is a little bit scary and frightening about functional programming. Like, for loops are very kind of concrete and obvious what's happening, and now you're giving away some of that control. But as you get better and better at functional programming, that becomes freeing, because you're tossing that problem away to someone else and relying on them to solve it so that you don't have to. So now I want to dive into a real example, talking about getting some data. I'm going to be using some data from the British family food data set, which has been surveying people for like 40 years now or something, or longer, asking them each week exactly what food have they purchased. And we're going to be using a bunch, I'm going to show you this in several different ways, this map function. And diagrammatically, this is what map does. Map has, in its simplest form, two arguments, a vector and a function, and it's going to return a list having called that function with each element of the vector. Or in baking style, if you have a bunch of cupcakes and you want to frost them all, it's going to frost each of those cupcakes with vanilla frosting. Okay, so let's take a look at some code. So what I've done here is, where have I put it? I have a data set that I downloaded from the British Family Food Survey that has one zip file for every year's worth of data. So I've got data here from 1974 to the year 2000. And what I want to do to start off with is just figure out, like, what the heck do I have here? And so the first thing I'm going to do is use a little bit of code just to get a list of all of the zip files. So basically all of the zip files in this directory, except for this one down here, which contains some metadata, which is a little bit different. And now what I want to do is I want to find out what's inside each of these files. And this is pretty easy to do if I've got a single file. So here I've just extracted the first file, and I've called that X. And in R, you can use the unzip function with the argument list equals true, and that will list all of the files inside that zip. And here, I just want to look at the name, so I'll subset that out. And so I can see for 1974, we've got household data, meals out, nutrient conversion factors, and so on. And that's pretty easy to do for a single file, but now I want to do it for all of these files. Now, I could, of course, write a for loop, but that's not what I'm going to be talking about today. Instead, I'm going to show you how to use the map function to solve this. And there's basically two steps. The first thing you're going to do is turn this kind of concrete instruction that says take this specific path and give me what files are inside of it, and turn it into a recipe. So there's two components to a recipe. The first component is that we use this tilde in front of it. That's basically, if you've used R before, you've seen this when you do modeling. The tilde basically means don't do something right now. I'm going to tell you, I'm going to give you a recipe about what to do. And then we're going to use a pronoun, this .x, which means, like, at the first, it's going to be the first path and the second path and the third path and the fourth path and so on. And so then I combine that with map. And so when I do that, I now get a list containing a bunch of character vectors that tell me all of the files inside all of those zip files. Now this is okay, but one thing that this list lacks is any way to kind of connect this back up with a zip file that it came from. Now, you'd hope that, of course, the 2000, the data for the year 2000 would be in the year 2000 zip file, but if you have worked at all with data, you should know that this is something that you should hope for, but never expect. So what we're going to do is make something a little bit more complicated. Instead of just having a character vector, I'm going to create a data frame where for each row in the data frame, we're going to have the original path of the zip file and then each of the files inside of it. So it's a pretty straightforward application of just creating a data frame or a tibble here, one variable called path, and one variable called file, which is just the code that we used before. So again, if I want to apply that I did that for one, but I want to apply that to every file. So I'm going to make this into a recipe. So I make this into a recipe by putting a tilde in front of it, and then using a pronoun, this is special magical .x, instead of the concrete actual x that I used previously. And then I can feed it into the map function. And now I'm going to get a bunch of data frames. Now, one of the things that's nice about map is that it always returns a list. You can absolutely guarantee it's always going to return a list. It's never going to automatically simplify your data for you. So in this case, we do want something simpler. We'd like it to be a data frame. And so we're going to use one of the map variants. And all of the map variants have the same form. They all start with map, the name map, and then an underscore. And we're going to create a data frame where each of the outputs becomes a row. So if I do that, now I get this nice data frame that's got 162 rows, one row for each file inside the zip file for all of these zip files. And so now we can check if each year is the same file. So I do a little bit of, I'm not going to talk about this today, but I'm just using this function called extract from the tidyr package that's going to carve this files variable up into two variables, a year variable and a name variable. And then I'm just going to count how many files are there with each name. And if we're lucky, there will be the same number for each name, representing the fact that every zip file is the same structure inside of it. And so if we do that, well, it's not too bad. They pretty much all of them have 27, which we should just confirm. There were 27 paths there, so there are 27 diary data, 27 household data, 27 meals out. And then we've got 26 nutrient conversion factors data, but in 1 year, it doesn't have data on the end. So not doing too bad, but we need to bear that in mind if we're going to load that nutrient conversion data in later. Okay, so now we've determined that all of these zip files have a pretty similar structure. So let's unzip them all. So again, unzipping one file is pretty simple. I'm just going to unzip this, and I'm going to say unzip it in a directory called NFS, short for National Food Survey. And if I navigate to that, you'll see we've now got those files for 1974. And again, I could, that's how it's easy to solve for one. I can turn that into a recipe by putting a tilde in front of it and then using a pronoun and then combining it with map. And you'll see this unzipping all of those files. You'll also see in the console here, it's returned a bunch of values. Now that's not something we really care about here. I mean, it's kind of nice that unzip tells you what files it returns, but we don't actually care about that, and having a bunch of stuff print out in the console is pretty useless. So I'm going to use another variant called walk instead of map. So walk is exactly the same as map. It works in exactly the same way, except it just throws its output away. So it's going to do the same thing. I could delete this directory. I have a little code up here. Delete that directory. You'll see it's now empty. And rerun that code, and you'll see that's unzipping all of the files again. So now we've got all those files in the directory. Let's read some in. I'm going to read in the meals out data set because it's pretty simple. Here is the data description that the website said that all the files should look like this. I think it's a really, really good principle when you're a data scientist to trust, but always double check what people tell you about their data. So what I'm going to do is just check that these files are as I expect. So the first thing I'm going to do again is I'm just going to make a vector of all of those files I want to deal with. So all of the ones that have meals out in their name. And this time I'm just going to start by looking at the first line. So again, I create, I just call it X, that's just got a single path. If I want to read a single line from a single path, that's pretty easy. I can use read underscore lines from the reader package and say I just want a maximum of one line. You can see straight away that this is a tab delimited file, and these are the headers. And again, I can repeat that using that same strategy, make a recipe by putting a tilde in front, using that .x pronoun and combining it with map. And I get a list of all of the first lines. Now in this case, a character vector would be a little bit simpler than a list. So instead of using map by itself, I can use another variant called map underscore CHR for map producing character vectors. And I'm not going to talk about them today, but there's a bunch of other variants that you can find in the help. So if I run that, I now get a character vector, which is a little bit hard to look at because it's got names. Let me strip those names off. And you can see this is the first line of each of those 27 files, and they all look pretty similar, which is good. And I can just double check that by using table, and it says all 27 of them look like this. So that's great. So I've determined that at least at this level, it seems like all of those files have the same structure. Now let's read them in. So again, easy enough to do. For a single data frame, we could use read underscore TSV, which reads in tab separated files. When I do that, it prints out the column specification. It just tells me how is it written all of these files, all of these fields. Well, it turns out they could all be integers, so I'm just going to create a little column specification to do that. The details aren't too important. But here I'm just reading them all in as integers. So again, that's how I read it in for one file, and now I want to do it for all of those files. So I turn it into a recipe by putting a tilde in front, by using .x, and then I'm just going to jump straight to using map DFR because I know I want to combine them all into a data frame. And so when I do that, I now get a data frame with about 800,000 rows and 8 variables for all of the 27 files that I care about in that directory. Now, if you look at this for a little while, you might notice that something is missing. And this is a pretty common problem, that you've got an important variable that is not stored in the dataset itself, but is stored in the name of the dataset. And in this case, that's the year. So there's various ways we could solve that just using functional programming. I'm going to cheat a little bit because in this special case, the vroom package, which is a really fast way of reading in datasets, provides us a little shortcut. So with vroom, you can give it a directory of file names, and you can say, well, I want to turn the path into this variable called path. And so now we've got this variable which tells me the source of each record. Again, I'm just going to use a little bit of tidyr, the extract function, to turn that into a year. So I've gone from the string that gives the path of the file, just extracted out the year, and now we've got a data set with all the information that you might care about. I'm going to take a quick look at it. I wanted to focus here on this kind of fairly common, fairly annoying task when you've got a bunch of different files inside of other files and want to read them all together. But I wanted to show you what that gets us to in the end, which is somewhat of an anticlimax given all that work. But this plot shows by day of week, by the log day of week, how many meals out were eaten each day of the week over the course of this data set. And there's two things here. So obviously, look, there's a striking drop here, right? We go from an average maybe three days a week, eating out 3 meals a week in the 80s and 70s, to eating out 1 meal a week from 1995 on. And this kind of dramatic drop, like, it is extremely unlikely that in the year of 1996, every person in England started eating out less. And so this probably represents some kind of change in the definition of this variable. And you'd have to go back to look at the underlying data, the underlying descriptions, to figure out what's happened there. The other thing I kind of looked at with this when I was looking at it, I was like, well, what does log day mean? Well, maybe this is day of week. And so maybe 1 is Monday. That probably makes sense, right? People eat out at least on Mondays, and then Tuesdays a little more, and then they eat out highest on Saturdays. But that sounds kind of plausible. So maybe this is day of week: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Until I looked at the number of school meals consumed per day. So many children in England get a meal as part of their school day. And when I looked at that, however, I'm pretty sure there are not very many children attending school on Friday and Saturday. So I suspect my initial conclusion is completely wrong, and these are not actually days of the week. I don't know what they are. I think they're relative to some other date offset, which is stored in another data frame, which I haven't had a chance to look at yet. Okay, so that was a whirlwind tour of using some functional programming tools to load in some data. The kind of key ideas here, we're using this map function. The map function takes a bunch of things. It takes a recipe or a function, and it applies that function or that recipe to each of the things in the input. Or if you like cupcakes, it allows you to take each cupcake and then frost them all in a single line of code. So that's the use of functional programming, kind of very much on the front end, like getting your data in. I think functional programming has another really cool use when you are generating reports, when you're communicating to other people. And so before we do that, I need to talk about one little aspect of map, and that is what happens if you don't have just one vector to map, but if you have 2 vectors. So just take a second and see if you can kind of imagine what the result of this is going to look like. And this is what it actually looks like. So map only maps over only breaks up the first vector it sees. It doesn't touch any other vectors. And so what we need is another function called map2, which takes 2 vectors and kind of breaks them up in parallel and calls a function with 2 arguments. And this is going to be really important for creating reports, because when you create a report, there are basically 2 things you care about: the subset of the data and the name of the file you're going to create on disk. Or again, if you want to do this with monsters, the advantage of map2 is it allows you to frost each cupcake with a different type of frosting. Okay, so let's have a look at this report I prepared earlier. So this report is a report about it's not a very good report, but it's a report about the Great British Baking Challenge using the fantastic Bake Off package that Alison Pressmanis-Hill put together. So this is an R Markdown document, which lets me mingle code and prose. And when I render or knit this report, I get this PDF. And so this is not terribly exciting, but it tells me for the Great British Baking Challenge, well, I should say season 4. Let's reknit that. So for the Great British Baking Challenge season 4, it premiered on August 20th, 2013. It had 10 episodes, and here I have a little plot of the ratings of that over time. Now, I've kind of set this up using what's called a parameterized report, so I could just change this one number here from season 4 to season 5 and rerun that. And in a moment, I will get a new PDF that has the data for season 5 instead of season 4. And, I could keep doing that for all of the seasons. That's going to get a little tedious pretty quick. So rather than tackling this by pointing and clicking, I could write a little bit of code instead. And so here I am just going to show you like what I was doing when I was rendering that document. I was actually running a function behind the scenes called rmarkdownRender. And that takes the name of the R Markdown document, which I called bake-off report. It takes a path where I want to save that. I want to call this season 3. And then it takes those parameters which I set up. And if you look carefully at my code, you'll see what my code does is a bunch of filtering just to find the records that apply to that season. So if I run this and look inside this folder, you'll see I've just generated that report I showed you before programmatically. So creating a single report is pretty easy, right? You just got to call rmarkdownRender once. But we want to do this for every single season. So first of all, let's figure out how many seasons there were. Well, I think this data, it's a little bit complicated, but the first 2 seasons of the Great British Baking Challenge were not available in the US, and this data has US data as well. So we just see seasons 3 to 7. And then where do I want to save them? Well, I want to save them in the Great British Baking Challenge folder with just a name called season dash the season number and then .pdf, because these are all going to be PDFs. Now, again, I want to solve this problem. It's easy enough to solve this problem for a single case, although you'll notice I have to put my parameters. In a single season, that's pretty easy. I just use the list function, which, surprise, creates a list. And I can do that for all of the seasons by using a map function, and again, making a recipe by putting a tilde in front and using the .x pronoun. So now I have a bunch of paths. I have a bunch of lists that defines the parameters for each of those paths. And now I can use this function called walk to. So walk to is to map to what walk is to map. So it's just exactly the same. I could actually, I'll use map to here. That's going to iterate over each path and each param, and it's going to call rmarkdownRender. The input report stays the same. The output file comes from the first argument paths. The param comes from the second argument params. And if I run this code, you'll see that this directory is going to hopefully fill up with PDF files. 1 PDF file for each season. Now you notice when this finishes running, this just gives me the paths of all of the files I just created, which I don't care about, which is why I make this a walk function, which is just going to throw away its output. And so now I can look at, say, season 6, and see, that's interesting. It's got some missing values in there. I'll pull up season 7 just as easily, or if the other thing I sometimes do is kind of the poor man's animated GIF, which is just use quick view and then slide through the different PDFs. And I think this reveals something interesting. I think there's a data quality problem because we're looking at the viewers. This green line is the number of people who watched it in the 7 days after it was published. And the pink line is supposed to be 28 days after it was released. It's a little suspicious that that's lower. But you'll see when we get to season 6, unsurprisingly, as you'd expect, the number of people who watch it in 28 days is higher than the number of people who watch it in 7 days. But not that much higher, suggesting most people watch it the week it comes out. Excuse me. Okay. So I've shown you 2, I think, useful ways of using functional programming. I use it a bunch all the time, but particularly when loading in data, when doing that data import phase, and also on the very opposite end, creating the reports that I can then send to individual people. And of course, you can imagine, like, I've got a bunch of PDF reports now on my individual computer. Like, what am I going to do with that? If I wanted to, I could create another script that then's going to email those reports to each individual, product manager or each individual customer, so that I can automate that entire process as well. So remember, for loops, I don't think for loops are bad. You should never feel bad about using a for loop. I think the challenge of a for loop is because every for loop has the same kind of repeated boilerplate, the duplicated code can make it hard to see the important differences. And on the other side, like, yes, there has to be a for loop somewhere, but why should you be the one to write it? Why not rely on someone else's code to do that for loop for you? So we talked about the loading in the data and creating model reports using the same basic idea, the same function map, which comes with a bajillion different variants that produce different types of output, like character vectors or data frames, or no output, like walk, and then comes with variants like map2 when you want to iterate over more than one vector. Now, if this talk has got you a little bit interested in functional programming, and I hope it has, two more places that you can learn more, two things that I've written that you can learn more. So the first is in my book about advanced R. There's a chapter called functionals, which is the technical term for these map functions and related functions that I have been talking about today. There are also other chapters on other parts of functional programming, like functional operators and so on. This is really good if you are, I would recommend advanced R if you are a more experienced R programmer, or you're experienced in another programming language and want to learn what's special about R. The other place you can go for help to learn more that I've written is in R for Data Science. The goal of R for Data Science is to help you become fluent in data science and R as quickly and as painlessly as possible. It's not totally pain-free, but as painlessly as possible. There's a chapter there about iteration, which talks more about for loops and more about introduces these functional programming ideas at a kind of level more focused towards doing data science, whereas advanced R focuses more on the kind of functional programming language side of things. Thank you. And
thank you, Hadley.
I just wanted to leave you with, the fantastic drawings are by Alison Hulse, who is a wonderful artist and an R user, and created these really, really awesome diagrams to help illustrate this talk.
All right, thank you, Hadley, for your talk on cupcakes and code. We'll head over to the Q&A portion now, and we've got some questions coming in. There's a handful around programming syntax and some of the function calls. So the first question is, what's the difference between the function map and the apply family of functions?
So at the level, so the question is about the apply family of functions in base R. The equivalent to lapply is, so the equivalent to map is called lapply, which is short for list apply. And at the level I've talked today, they're basically identical. The main advantage of map is that, so I've shown you, I showed you this kind of syntax in map, this recipe syntax, which is a special feature that purrr provides, which is just a shortcut for writing an anonymous function. And so the first thing that lapply misses is that it doesn't have this, so you have to write out this full syntax, which is absolutely fine. Like, if you understand functions and how argument order works in R, argument matching works in R, lapply and map are basically equivalent to you. But I think map is a little bit easier to learn when you're starting. And then the other payoff is that the kind of family of functions provided by map is by the purrr package is more comprehensive than the family of apply functions. So they allow you to generalize a little bit more readily in various directions that you'll eventually hit. All
right, we have another question here. How do map and map2 deal with errors? In a for loop, this person can use the try catch in a case of a problem for a specific value, missing data and so forth.
really, I want to show you this because this was a slide that got cut, just because I love this picture that Alison drew of this problem. But yes, that's a really big difference between functional programming, and there is a really useful technique to solve that. Oops, that's the first edition of Advanced R, which I think I talk about in here somewhere, function operators. So there's a function called safely, which basically turns any function that throws errors into a function that never throws errors, but just returns them in a special data structure. So you can use safely to kind of continue to, so it means that everything will succeed. You will get a list back. That list will tell you for each input, did it succeed or did it fail? And then you can take actions based on that. But that's definitely one of the weaknesses, or one of the new things you have to learn when you switch from for loops to functional programming, is you have to learn some slightly new tools for handling problems.
All right, and also we've seen the .x syntax a few times, and there's a few questions about elaborating on that a little bit further.
Yeah, so again, this is just like a special, let me construct this a little bit. Okay. So this is just kind of a special like shortcut. It's like syntactic sugar. The point of it is so you can type as little code as possible. So what happens is behind the scenes, what the map function is going to do is it's going to convert this code into a function. And this sort of function is called an anonymous function because I haven't assigned it to anything. I haven't given it a name. But you can see that that's quite like a lot of typing. Now, in this specific case, you could reduce it still further if you understand exactly how function calls work in R to this simple case. But the idea of this like recipe is so that you can learn how to use functional programming kind of ironically without having to learn functions. And I think that's sort of a weird idea, but I think the ideas of like iteration are so powerful and useful that you need to be able to use them before you've fully grokked how functions work in R. And that's the idea of this special syntax, this special kind of recipe syntax. It just lets you express the idea, I want to do this thing to something without saying, do it to something right now.
All right, and another question we have around some syntax here is what's the difference between the .x argument in purrr and the dot argument from dplyr?
So dplyr technically does not have a dot argument, but Magritte, which provides the pipe function that we talked about briefly, does. So with a pipe, you can, I can't think of a great example off the top of my head. You can kind of, by default, so basically that they're both kind of like shortcuts. They're like syntactic sugar that allow you to do kind of weird and special things. Originally, purrr actually used, and you can actually use the dot still in purrr, but that's super confusing because then it's hard to tell, is the dot meant for purrr or is the dot meant for Magritte? But basically, they kind of play the same role. They're kind of about like being pronouns, like referring to something. In purrr, they refer to elements of the vector. With the pipe, they refer to the thing on the left-hand side. They just and being able to explicitly refer to those pronouns gives you the ability to express some ideas that are a little bit harder otherwise.
All right, and we have another question here about the map function as far as performance goes. Like running, does it run in parallel on multi-core or on clusters? when the library runs the function over the data vector, is it still single-threaded?
So it does not. It is single-threaded, but there is this package called purrr, which is a combination of the purrr package and the futures package by Henrik Bingstone, which does do multi-core. So basically, you can just use the purrr package and switch from using map to future map, and then that will run that over multiple cores or multiple processes or any of the backends that the future package supports. And there's a bunch of different backends you can use through the future package. So purrr doesn't do multi-core out of the box, but you can easily use it with this wrapper called purrr by Davis Vaughan, which uses the future package by Henrik Bingstone, which provides this really nice abstraction over the different types of parallels that you might want.
All right, I think that we have a slightly higher level question here. What is your workflow regarding .r file scripts versus the R Markdown file? Is the work done in R and then copied into R Markdown? Do you ever initially explore and transform the initial data in a Markdown file?
So often what I do is I do a bunch of writing in an R file, and then I start writing comments where I'm like, well, I did this transformation because, and then I write a bunch of comments, and I write a bunch more, and then I'm like, oh, I've now, like, there's more text in my R file than there is code. Like, why didn't I, and this happens to me every time, why didn't I start out with an R Markdown file? So to me, the trade-off is if you're writing more code than prose, use a .r file. If you're writing more prose than code, use an RMD. And I think in most like data science projects, you end up typically writing more prose than code because it's like easy to do it. It's harder to explain what you're doing. So I think generally, you know, I probably recommend starting off in an R Markdown file most times. I just always forget to do that.
Right. And another question, when writing code for collaborators with little programming background, how would you recommend explaining and documenting a functional approach? I find myself defaulting to clunky iterator patterns because it's sometimes easier to verbalize what's happening.
Yeah, I think that's, I mean, I think first of all, that's fine. Like, I think of like code as a medium of communication, not just the computer, but to other people. And whenever you are communicating something, you need to keep the needs and the knowledge of the audience in mind. And so I think that means that sometimes you will, when you're sharing code with other people, you will write code in a different style to the way you would write it for yourself. And then it's sort of a tricky balance of like, you need to think like, is it going to be easy for me just to use for loops? And if it's like a one-off project, like it, probably educating your collaborators isn't worth it. But if this is something that you're going to do in the long term, it might be worth, instead of like having to rewrite your code into something that they can understand, maybe you can help them upskill a little bit and help them learn how to use functional programming in their own tools. And I think that's just something you have to think about explicitly, because code is a medium of communication. And whenever you're collaborating with someone else, you have to think about them, not just yourself.
All right. I'm afraid we're running out of time here for the webcast today. I'd like to thank Hadley again for his insightful information presented here, and for answering our questions. I'd like to give a special thanks to each of you for taking the time to attend and participate today. This talk was recorded and will be available online in a few days at learning.acm.org. You can find announcements on upcoming talks and other ACM activities at learning.acm.org and acm.org. On behalf of the ACM, Hadley Wickham, and myself, Andrew Conklin, thanks again for joining us, and I hope you'll join us again in the future. This concludes our talk.